His presentation will be on fatigue behavior of additively manufactured Inconel 718 produced by selective laser melting. Mr. Klaas, you have 15 minutes, and then we'll have discussion after this.
Okay, so I'm Klaas Solberg from the Norwegian University of Science and Technology, working in the group of Filippo Berto. I will present a work I've done on fatigue behavior of additively manufactured Inconel 718 produced by SLM. So the outline of my presentation is first some introduction, then I will say something about the material and the experimental procedure. I will present some results and then give a conclusion. So additive manufacturing is a layer-by-layer manufacturing method where you can produce all kind of complex components in different materials. You can do, for example, on-demand production, so you don't have to have large stocks of components. And there is like this figure where you compare conventional manufacturing to additive manufacturing, where the y-axis is cost and the x-axis is geometric complexity. So if you increase the complexity of the component for a conventional manufactured component, it will be very expensive and not able to produce it. But by additive manufacturing, you would not increase the cost, and you could also increase the complexity without any limits. So you can have all kinds of internal structures and these kinds of things. But of course there are some challenges. The material quality is not yet fully understood, and there are, for example, surface discontinuities and porosities inside the materials, which we have to kind of deal with. Selective laser melting is a method you use for producing metals. You have a powder bed, and layer by layer you sinter powder together, so it forms a complete component. This is some example we have from my university with the student race car. They are producing, for example, brake caliper and the uprights, and they are topology optimized. So you can see from these components that in many cases you would produce something by additive manufacturing, machine it, and you would have some properties. But in this case, it's not possible to machine it because of the complexity. So it's very important to understand how the surface is, what is the state of the surface, and if there's any discontinuities, etc. Okay, so I've been working on notched specimens to see the effect of both building angle and the stress intensities. I've been working on Inconel, produced by selective laser melting. No post-processing has been done to these specimens. So there are no heat treatments, no machining, nothing. This is just the as-built state. And also there has been no support structures, as you would normally have to kind of get a good material quality. So we kind of see the effect of not using support structures. They have been built in the set direction, standing, and there are 3 different geometries, one which is unnotched, and there is a semicircular one and a V-notch. Inconel is a nickel-based superalloy. It has high strength and corrosion resistant at elevated temperatures, and it's used for example, aerospace industry, oil and gas, turbine blades, or extrusion dies. One of the problems with Inconel is that it's hard to machine. So with this kind of additive manufacturing, it's a good match because then you will not machine it anyways. And this is the composition of the material. We looked at the microstructure of the material. In the top plate, we see the cross-hatching from the building, and we can see elongated grains in the building direction, and also we can see the cross-section of the melt pools. So this is the standard as-built material. So we have been performing uniaxial fatigue to these specimens by load control with a loading ratio of 0 and a frequency of 10 Hertz. Sinusoidal loading in room temperature tested on a servo-hydraulic system. Okay, so these are the fatigue data we obtained. As you can see, the unnotched specimen has a higher fatigue strength than the two notched specimens. This KT is the elastic stress concentration factor for the specimens, and we can see that there is a kind of correlation. The semicircular specimen has a higher stress concentration factor than the unnotched, of course, and also the V-notch has an even higher stress concentration, and there is a correlation in the fatigue life. However, when we evaluate the fatigue notch reduction, there is a higher fatigue notch reduction for the semicircular than the elastic stress concentration, which is it should not be possible, because you would have a notch sensitivity below 1. No, yeah, above 1. So for the V-shaped notch, we have the values are within what's kind of expected, but for the semicircular, we have a higher fatigue notch reduction. So we had to look into this, and then we went, yeah, okay, first I'll compare the unnotched specimen. These are some other results reported for also uniaxial fatigue, hourglass-shaped specimens. And we can see that there's, I've corrected it with the mean stress correction. And there is, in the fatigue limit, there is a good correlation. And also there is a bit slight different in the slope, but it's kind of in the same range. And if we look at the fatigue notch sensitivity for some normal Inconel paper from Nitsitani, we see that the elastic stress concentration is a lot higher than the fatigue reduction factor. And comparing this, we would see that the semicircular one has the higher fatigue reduction factor. So we went to fructography by SEM. This is the unnotched specimen. The crack is propagating from one side with first striations, and then the final rupture is ductile. But it's from one side, so there is not a lot of effect from both sides. This is the V-notched specimen. It has, of course, a stress concentration on both sides, so the crack will propagate from both sides. And we see that the crack is initiated from lack of fusion in the surface. And we can also see, I will show this also later, that there are some unfused particles in the crack initiation area. So for the semicircular specimen, the crack is propagating from only one side, which is weird when you have the double notch component. And there is also a lack of fusion defect in the surface. So the top two pictures are from the unnotched specimen. We can see, for example, a porosity where the crack is growing through it, and we would see the striations interacting with the porosity. And the right one is the surface defect, which initiate the crack growth. The two lower ones are from the notched specimens, and we can see lack of fusion and the unfused particles, which are of size approximately 30 microns. And there was a larger scatter in the unnotched data. So we looked to the surface defects and found a kind of correlation. There is a larger surface defect for the sample failing earlier than for the sample failing having a longer life. And also this is the case for the semicircular one. There is a kind of surface defect along the whole area or along the whole edge, and also a correlation between the surface area and the fatigue life. Okay, so we have looked at the fatigue strength of different notch geometries, and this fatigue notch reduction factor was found higher than the stress concentration factor for the semicircular specimen, which is very weird. Cracks initiated from surface defects in all specimens, and the cracks propagated from one side in the unnotched specimen and the semicircular specimen, and from two sides in the V-notch. And also the correlation between the size of defect and the scatter has been found. Thanks for your attention.
Thank you, Mr. Klaas. So, questions from the audience? Microphone, please.
Of the SLM-produced Inconel 780 with that of conventionally processed 780?
Yeah, I mean, I have it in... Okay. Where is this pointing? So this one is comparison.
Okay.
So you see that the fatigue strength for the conventional one is around, let's say, 500 for the unnotched specimen, and this one is 250.
Okay.
So, but for convention, like for data reported on conventional Inconel, it's always heat treated, and then you would have the gamma prime phases and these kind of things, which will strongly increase the fatigue life. But mine specimens are only as built, so you don't have these kind of phases.
And another question, if I may, did you see a difference in surface roughness because you printed them vertically in the notch? I would expect that the overhang part is different than the underneath part.
Yeah, there is a large difference in surface roughness.
And will this affect the result of your test in any way?
I think it will not affect, because the surface roughness is one thing, but it's always initiating from lack of fusion defects, which are acting as cracks, and I think those will be more dangerous than the kind of wavy surface, which will just act as a notch. But yeah, for sure the specimens, I guess, will be failing from the area where you have printed in overhang.
Thank you. Next question.
You mentioned heat treatment, but that all of these tests had been done in the as-built condition.
Yeah.
Does that imply that you're planning to use as-built components without heat treatment?
I mean, in some cases, if you have a really complex geometry, which has been like the ones I showed you, then you're not always able to heat treat stuff because it can buckle and it may be hard. So of course, you wish to heat treat it, but in some cases you're not allowed, or you're not able to do it, and then you have to kind of. We're starting it with as-built and then going forward.
Next.
As you mentioned, it's weird to see that the KF factor is higher than the stress concentration factor.
Yeah.
Do you have any clue how does it comes? Because all the literature is starting from Neuber in the 50s to today say that the KF might just reach the stress concentration level.
So when we have evaluated this, we have used the geometry like the nominal geometry, as we see in the figure. But for additive manufacturing, I mean, we're not machining this to be a perfect surface. So the lack of fusion defect will, for example, act as a crack, and you would have the stress intensity factor from this. So based on what you're able to measure, you will kind of get a really high stress, or a stress intensity, rather than a stress concentration, because of the lack of fusion defects, if that's clear, or if it's... Is it answering your question?
Okay. Interesting. Thank you.
More questions? Okay, then thank you for the presentation again. And this was our last speaker today. And I would like to thank all speakers that we heard today for their contribution, and also thank you for your questions and your contribution to this discussion. With this, I'm closing this section. And just to inform you, 11 o'clock here we have a coffee break. And then 11:30 we have a closing section in this next room. Thank you again and see you next time.